How do we predict which?
How would we predict where the unstable equilibrium would be?
Well, you don't predict, you figure it out. So we know that this is the stable equilibrium here. This particular, I can't read it anymore because I've only got one color. But this particular graph only has 4 equilibria. This one, this one, this one, and this one. These 3 are all unstable.
Okay.
This one is stable. This one only has 1 stable equilibrium, and it's got 5 possible. 1, 2, 3, 4, and this one is stable. It's the only one that's stable.
For that drawn-in graph.
Loudly again, I'm a little deaf.
Sorry. For that drawn-in graph, could you tell me why, like, the stable equilibrium isn't the point below it? Is it the intercept right below it?
Sure. So the question is, if this graph, I'm just going to clean it up a little bit. Right? And your question is, why is this not a stable equilibrium? All right, so talk to me biologically about what's happening at that point. What's the density of species 1? 0. If the density of species 1 is 0, what's species 2 going to go to? Its carrying capacity. It's just going to walk up this line to its carrying capacity. Rebecca. Loudly? Okay, before we move on topics, do people have other questions about species coexistence or lack thereof? This one? Right, well, ideally, I mean, these have numbers. These have real values. So ideally, you actually have some numbers to plug in here. You could have all sorts of complicating situations where where one of these two wound up between them, but neither one of them should reach its own carrying capacity. You're right, there is an arbitrary nature to this. Question, I don't know your name at all. I don't know your name either. Caroline? Oh.
Would we ever see any situation where there's like an unstable equilibrium where like a predator and species 1 and 2 exist, and a perturbation in any direction would send it to like one species?
Absolutely. Because I've shown you 3 of the 4 possible graphs now. So there's one other graph. You want to do it?
That's a saddle point.
Yeah, that's a saddle point one.
Let's do it. This is some expert camera work.
So what if I had, oh hey, there's another color.
This is my problem.
Life is really
I
rich.
should have been doing this every lecture, basically. We're doing the next one. Yeah, we are. Yeah, we
Alright, you can see the blue? Alright, so this one, you know these upper right, lower left corners are going to go in. So it's very tempting to say, we've got some kind of stable equilibrium going on. Well, let's actually look at this. So here, if I start here, I am above the isocline for the first population. I am below the isocline for the second population. If I add those vectors, where do I go? That's right, upper left. And we can do the same thing here. Here, I am above the isocline for the second population, and I am below the isocline for the first population. So I go that way. So if I've got 5 points again, this is an unstable equilibrium. This is a stable equilibrium. And this is a stable equilibrium. And where I wind up depends on where I start. It's chaos, I tell you. There's something very close to it. Now, one thing I want to correct, you talked about predator-prey relations. There are no predators in these graphs. These graphs are only about competing species for some common reason.
stable because it has a tendency to move away from it, not towards it.
How do you become stable and unstable? Like, I think there's like they're all going in different directions.
Well, so anything here is going to move kind of this way. anything here is going to move kind of this way. And then once you're here, you're going in these opposite directions from this unstable equilibrium. That's why it's unstable. But then if you want to, the easy thing to do is again say, what happens if we're sitting right on that line? What happens if we're sitting right on that line?
Go to the current capacity.
Right. You know what? So that's going to be the stable equilibrium. But we can ask the same thing here. What happens if we're sitting right on this line? We go to this carrying capacity. So the short and kind of unsatisfying answer is the way you know is by drawing lots of little vectors. Joey, I think there's one person whose hand was up before yours, but I don't see either they're hiding or go ahead.
Okay, can you do that in T about?
So that should tell you something, right? The short answer is no, you can't really. You have to know a lot more specifics about the system to do the NT versus T, because where you wind up totally depends on where you start. If you start here, you're going to wind up in a different place than if you start here. Right? So that's the problem with this one. That's the problem with unstable equilibria in general. Where you wind up depends on where you start. My guess, and I'm pulling this from the recesses of my brain, is that if you start here, it'll wind up there. And if you start here, it'll wind up there. Yeah. Yeah. So there isn't an easy way to do the NT versus T graph for this unstable equilibrium without doing some math along the way. And I'm not going to ask you to do that kind of math. Perfect.
So for this one, there would be like multiple NT versus T graphs,
Right.
depending on like what,
Right, where you started. Right. It's a great question. So if you're balanced right at that unstable equilibrium and there's no perturbation, you can stay in that unstable equilibrium. That's not going to happen indefinitely. Sooner or later you're going to get bumped someplace, and if you get bumped more toward this side, you'll go to this stable equilibrium. If you get bumped more toward this side, you'll go to that stable equilibrium. So it's a really unsatisfying answer to say, it all depends, but it turns out it all depends. And I think this is actually fairly biologically plausible, this situation. So there are probably lots of cases where we have something that looks like competitive exclusion, but which way it's competitive exclusion depends on some more or less random factors. Scott?
Could you just explain the difference between the stable and unstable equilibrium?
Which part of it do you need?
I don't understand the difference between the stable and unstable.
So the question is, what's the difference between a stable and an unstable equilibrium? And the easiest way to think of this is, and about half of you, I think, by this point have heard me say this before. The easiest way of thinking about this is that you can have a bowl, and in the bowl you can have a ball. Except this ball is actually inside the bowl, so I'm trying to do little hash marks so you know we're looking through the side. If you've got a ball in a bowl, and you bump it, you perturb it, it's going to go back to the bottom of that bowl. That's a stable equilibrium. Right? So if you perturb it and it goes back, it's stable. If you have an inverted bowl, and on top of that inverted bowl, you have a ball, and you perturb the ball, it's going to go further and further away from that balance point. And if it's going further and further away from that balance point, it's an unstable equilibrium. So if you bump one of these points and they go back, it's stable. If you bump it and it goes farther away, it's unstable. I'm hearing a lot of chatter, which makes me think that people are still confused about something. This is literally a good time to ask questions. This is the best time to ask questions. So just because I'm hearing a little bit of murmurations, not in the sense of starlings flocking, this is a really excellent time to say, Philip, I have no idea what the hell you're talking about. Could you please go over this one more time?
So in the competitive exclusion graph, I'm sorry, like say that you start with the unstable equilibrium with the other carrying capacity, then you just prefer to go back to the carrying capacity. Since the N2 in that case was 0 of that carrying capacity, would it prefer to
Yeah, so there are two questions here. One is, the first thing is I said, that when you have the unstable equilibrium, it can look like competitive exclusion, but it's not really the simple form of competitive exclusion. The second thing is, what would bump that system away from n whatever equals 0? And the answer is, yeah, some kind of immigration event. And there are lots of examples of that. Some of them are famous. Some of them are everyday. Right? It's just, it could be a crazy immigration event like cattle egrets getting blown from Africa to South America in 1871 or 1877, right? And that totally changed the landscape of birds in the Americas. Or it could be something, lame, like a particular species of mosquito larvae winked out in a small pond, and then the next year they come back. And you told me your name, and I just forget. I'm sorry? Regina.
So in the graph that's up there right now, in the graph that's on the PowerPoint right now, what was the NT versus T graph when you started in the top right?
Okay, that's a really good question. And the beautiful thing about this one is that it's going to wind up in the same place no matter what. So if we've got time, that's supposed to be a T. It looks like a 4. Let's try it again. If we've got time, and here is our K2, because I made that blue before. Here's K1. And we were starting someplace up there. We're starting above the carrying capacity for either of them. That's something to notice. And I'll arbitrarily say we're starting right around there. We're ending below the carrying capacity for each of them, right? And this is stable. So at some point, our second population is going to hit some place below K2, and it's going to stay there. So that's N2. Our first population is also going to hit some point below K1, and it's going to stay there, N1. So we're going to go from up here to some stable point, because once it's stable, it stays the same over time. That's why these are flat. And it'll probably do something pretty simple like this. All right, does that make sense? But whether you start with N1 and N2 here, with N1 and N2 here, with N1 and N2 there, or any combination, they're going to wind up at the same stable equilibrium for this graph. And that means that you've got coexistence between two species. That's what's important. It's not just how to manipulate the graphs to make it look cute. It's saying, what does this mean biologically? And what this means is that we've got some biological conditions that lead to coexistence between two competing species. Jess? 31 in this lecture?
Can you explain about the pyramid with the bacteria and fungus? Can you explain the question marks and why it's the question marks?
Yeah, I'll tell you my shame on that.
This is the one I was.
All right, so this is a famous story, and this is a story that's been around for about 10 years. And ants, we've known that ants that farm, some ants that farm funguses, not all ants, some ants farm funguses. That's something we've known for 25, 30 years, maybe more, right? And it's pretty cool, right? So you've got these leafcutter ants that are growing funguses and eating the funguses, just crazy. It turns out many kinds of ants harbor bacteria, or actually in some of them it's another kind of fungus, but a lot of the bacteria, they harbor them on their body. They basically have biofilms on their body. And the biofilms grow in particular places. We know that different ants have different biofilms. We know that they have certain structures that promote the growth of these biofilms. So people are saying, well, why do they have these? It sure seems like there's some mutualism between the ants and the bacteria. Right? They're fostering these weird biofilms on their body. People used the biofilms to see if they had antibiotic properties against yeasts, right? To see basically if they kill yeast. So they grew up yeasts on petri dishes, put these biofilms on them to see if they killed them, and they did. And so the story from about 2005 until just a couple years ago very rapidly grew that not only were